This is Matthew Trujillo. I'm going to be going over my quiz number 3. I'm going to be talking a little fast because there is a time limit. I already know I'm going to go over it. Anyways, the question says that there are two switches that are closed for a long time before they open at t equals 0. So that means when t is less than 0, the circuit's going to be in a steady state process. And we know we are dealing with a step response because of this portion of the circuit right here. We have a capacitor, a resistor, and an independent source. Those are the three things we need for an RC step response circuit. Right. So what is step response? It is a way to calculate either the capacitive voltage or the inductive current as a function of time. And we know that this method needs three parameters: an initial value, a time constant, and a final value. Now, these initial and final values, we would either find the inductive current or the capacitive voltage, depending on if we have a capacitor or an inductor in our circuit, right? And these bottom four show the four cases of step response, and these top two show the two cases of natural response. And the difference between these two is the presence of these independent sources, right? And the solution is going to be in this general format right there, right? So going back to the question, it says we are looking for the energy dissipated in a resistor and how long it takes to dissipate some energy. Right, so we know that energy is the integral of power, and we know that power is, well, we know many equations, but we're going to use V squared over R, voltage squared over resistance, because we have a capacitor, and for capacitor, we solve for the capacitive voltage. Right, so we're going to use the capacitive voltage in our equation. Right, so the first step would be find the solution of the circuit. First of all, it is a step response. So getting started, we just got to define the capacitive voltage, and that's just by doing a positive and a negative terminal around the capacitor. All right, so to solve for the first parameter, we're going to solve the initial value first, right? So for there, we redraw the circuit for the time is less than 0, and remember, this is where it is in steady state. That's why we don't see the capacitor in there, because in steady state, capacitors are seen as opens and inductors are seen as short circuits, but we ain't got to worry about that right now. We got a capacitor. All right, so we have our two switches that are closed, right? And we have these two resistors that can be, whatever, because they're in parallel. So I'm going fast. We got to explain this. Come on. These two are combined into this single resistor right here, right? And we do not want to add this with the 1.2. They are in series, but these two have the same terminals as the capacitive voltage. This one is not associated with capacitive voltage, so we're going to ignore that for now. We have an Ohm's law right here of the VC, which is of the resistor, which is the voltage through the resistor, and it's going to be negative because we drew the current going that way, and we have the capacitive voltage going also this way, therefore it's going to be negative. We have a KCL around this loop going this way, so we have the negative 75 minus the capacitive voltage, and then we're going to add the 1.2 times the current. That's going to equal 0 because there's all a loop. It always cancels out, right? And this is exactly what I wrote right here. I just wanted to reiterate what it says, right? So once in this equation, we can solve for IA because it is the only variable in there. So IA is going to equal 9.27 milliamps. Right, now that we know that, we can plug this into the original equation. I did that right here. And that's going to be our first parameter, our initial value, negative 63.8. And that is VC of 0, because capacitors cannot change voltage instantaneously. And since it's in steady state, we're going to assume that this is the closest we will get to the capacitive voltage at time equals 0. The next parameter is the time constant. And we do this by redrawing the circuit for the time after 0, after the switch happens. So we have the switches open and our capacitor is back. It's no longer in steady state. So we can ignore this side of the circuit because it's open, simplifying it only to this, right? And the time constant in our circuit, we have an RC circuit, so we just got to multiply the equivalent resistance by the capacitance. And we only have one resistor, so we don't have to find it. Equivalent resistance. It's already given. So we multiply these two values right here. That's going to give us 19.2 milliseconds for our time constant, our second parameter, right? And our last parameter is the final value. We're gonna use the circuit for the time after 0 again, right? And we're gonna do a KCL of this top node right here. We drew two separate two separate currents, even though it is really all one loop, right? But since there is no source, there is going to be no current. So the sum of these two currents is going to equal 0, right? And we're just going to rewrite this. We change the resistance, the current through the resistor as a rewritten ohms, and we learned this. We learned this equation. We learned about capacitors at the beginning of the semester. We denoted that VC and V1 are two separate voltages, but in reality they are the same. They're equal to each other because they have the same nodes. They share the same nodes, right? So that's all we did from here to here. We just made it clear that they are the same, right? And from here to here, all we did was plug in our known values. But for this equation right here to be true, VC has to equal 0 because the other values are actual values. Therefore, we're going to use this as our final value. So our capacitive voltage final is going to be 0 volts. Right now, with all these parameters, we just got to plug them into our general format, and that's going to be this equation right here. All right, so moving on to actually solving our problem. First, we need to find the power dissipated by that 8 kilo ohm resistor. We discussed which equation we're going to use. I didn't write it right here, but imagine there's a C there for capacitive voltage, right? All we got to do, this is our general equation we just found, and we just plug that into the power equation. Once we solve that, we get this equation right here. That's going to be our power equation. The power is going to be the power dissipated specifically by the 8 kilo ohm resistor, right? And to calculate the energy dissipated for the 10 seconds after the switch occurs, all we have to do is take the integral of this equation of time. So all we got to do is plug this in here, and the initial time is going to be time equals 0 because that's when the switch occurred, and our final time is going to be 10 milliseconds after the switch, which is what the question's asking for. And once we plug this into a calculator, we get that the solution to part A is 3.125 millijoules. Now, solving for part B, we have to find the initial stored energy, and with that, we use the equation that we learned at the beginning of the semester when we learned about capacitors, this equation right here, right? And we're going to use the VC of 0 because we're searching for the initially stored energy, sorry. Once we plug that into a calculator, we get 4.88 millijoules. We know we are trying to find how long it takes to dissipate 75%, so we just got to multiply this value by 0.75, and that's going to give us 3.66 millijoules, right? And to find how long it took to dissipate that much energy, all we got to do is set the equation that we used earlier, set it equal to this 3.66. It's in millijoules, so we got to multiply it by 10 to the negative 3, right? And we're going to leave the final time just as t because that's what we're going to search for. And I did these steps by hand, but in reality, all we got to do is plug that into a calculator that's capable of doing that. And that will lead us to our answer, where the time it takes to get to 75%, to dissipate 75% of that initial energy is 13.39 milliseconds.